Okay, so let's talk about so those measures on the performances. So, and in the last video, we talked about the concepts of all these metrics to measure these kind of um, and performance of the models. So in this video, I'm going to using one very classic examples in for the of the MNIST data set to illustrate these kind of idea of all different performances of these machine learning and um, models. And also, I'm going to demonstrate with various different metrics, and sometimes I will talk about which metric is relatively making more sense. However, the others might not be making sense. So there's a lot of trade-off for choosing different kind of metric here. So this is the very classic data. It's called MNIST data set. It has 70,000 images, which has a 28 by 28 pixels. So this is basically has been studied so much. This is basically called like hello world of the machine learning. So that basically, if someone come up with a new classification algorithms and they want to curious how it performs, they will perform on MNIST to see how good it is. So this is and basically a very standard data set. So you can download this data set right here. It actually will be like the shape of this MX data is already flattened out. It's 70,000 by 784, which is pretty, so like 28 by times 28 is 784. So this Y, I mean, it's like basic tells you the digits of this corresponding images. So you can do this plot right here. So the way to plot this image is I'm going to reshape into 20 and reshape back into 28 by 28. So this is the and the pixel values of this an image. You can and use IM_show to actually to see this image. And also, and we can see this is actually a 5, and we can just and the key in the Y0, which is to output the label. The label is actually the 5 as well. So I mean, this tells you so the true label, and this is the the image. However, we are not using this image in the form of 28 by 28. I'm actually and flatten this image out to be like 1 by 784. This is actually the vectors that we are using right here. And of course, you can plot and all these images as a block of 9 by 9, and each of that will be 28 by 28. You are getting 81 and digits like that, right? So you can have some idea and what kind of image we are looking at. And you can see a lot of images of digits is quite hard to and to make and decision here. For example, right here. So this is actually and look at G. I think it's corresponding to 9. Some of that is it's quite hard to distinguish as well. Like this 2 right here. Some of handwritten digits in MNIST data set is pretty like sloppy. And a lot of cases will be hard even for human beings to make such predictions. So what we do is we're going to split this data into training and testing. So basic idea, and we're going to talk about how, and we have talked about this. So we need to split this data into training set and the one holdout set. And sometimes this holdout set here can be used to tuning the parameter as well. Sometimes, and this is going to be just solely as the like test set, just to use once to measure the to just measure the performance of the models. I mean, it depends how you like do this, but usually this, I mean, if we were talking about testing data set, and this is the data set actually we sit there, and we're not going to use that until to the end of the models. Okay, so let's try a training and we have talked about the binary classifier, and the binary classifier is very and basically fundamental things to every other like classification problems. So let's try a very simple and binary classifier trying to identify just one digit, which for example the number 5. So this is called 5 detector. So this is just give you some idea to see and to distinguish the digits between just two classes, 5 and a non-5. So what we're going to do is we're going to create this target vectors based on that. So what I'm going to do is my y train 5 is like that. This is my y test 5 of that. So if it is true for all 5s, it will be false for all other digits. So that will be 1 if we hit 5. It will be 0 for other digits. So this is a really good starting point to using the stochastic gradient descent classifier. It's basically called SGD classifier. So this is basically is actually you can think about as a logistic regression. I think it's like, okay, let SGD classifier, and you can have a look at that. What is this precisely? And what kind of the method? Yes, I think they are using like the default is I think they are using linear SVM. That's the default. Yes. So Hinge like gives the so linear SVM. So basically that's the default of the so methods. So there are like other methods that we can use, and if we're using different methods, it actually and the corresponding to different model. For example, if we're using log loss, that corresponding to and the logistic regression, it is actually a probabilistic classifier, and so on. They are like all different things that you can and use and work on here. All right, so this is basically and like the SGD and a classifier doing like if you don't specify that, we are using the linear SVM. So this is and a classifier is actually capable of handling very large and data set very efficiently. And because we are using the stochastic gradient descent methods to actually optimize that. I think this also mentioned about the methods, the algorithm to do this. Yeah, like with the stochastic gradient descent learning. So this is much and very robust and very efficient. So and it can handle this like and a very and a large data and efficiently. So what they basically do is they are going to an example of this training like instance independently one at one time. So that will be very suitable for online learning as well. So okay, so let's just so like by default that's linear SVM. So if you run this like SGD classifier, this random state, it's you just trying to fix the random seed and such that it can reproduce this result easily, and you do this simple fit, and you do this predictions, right? So this some digit that we already did, which is this specific digit right here, some digit, which is the first data of that. In fact, the output is actually true. That means this actually predict this to be 5, which is good. That's and that's exactly what we I expected. Okay, so and we can like using this whole thing to measure the performances. So the way to use this to measure the performances is we are using cross validations to measure the performance. So this is a function called cross-val scores. It actually evaluate our SGD classifier models by using k-fold cross-validation. We have talked about the k-fold in the past video. Here, k is chosen to be 3. And this is what I'm going to say, okay, so this is my SGD classifier. this is my training data. This is, the target variable, and the we're trying to do threefold. And the scoring method is just we're trying to score this with accuracies. So if we do this k-fold cross validations using this cross valid scores, so basically, so right here, this sentence just trying to explain what is the k-fold cross validations. This actually will give us 3 different validations values. One is 0.95, one is 0.96, one is 0.96. So basically, these 3 values are quite close to that. And you can see it, and the first sort, looks pretty good. In fact, looks pretty straightforward as well. In fact, you can also using and implement this cross-validation scores very explicitly by doing the stratified and sampling here. So this is basically the exact code. So if you want to implement these functions explicitly, and rather than using this function right here, this is how you actually do this k-fold cross validations from scratch. Sometimes that would be a good idea to do so, because you might need to do some tailed examples here. But this is just the way that you have a good understanding and what we are working with this k-fold cross validations here. So you see right here, so and this and the scores is precisely and the same. So this just tells you, and they are doing exactly the same things as this piece of code is doing. Okay, so this is give you some idea. But usually we don't do that. We just call this one single line function of the cross-validate scores. It just did all these things for you. If you actually want to find out the average of these 3 validation scores, you can just call numpy mean of this array. It gives you the average validation scores. So this average validation scores can basically give you a very good approximation for the generalization errors. All right, so next, okay, so and then let's also look at the very dummy classifier. So basically, and we do is just classify each single image as the most frequent classes. So in this case, it would just be negative classes, because 90% of the images being non-5, only 10% of images being 5. So if we do this, you will find out this actually predict any value to be false. But if you do something like that, you can also do cross-validation here. You're getting almost 91% of accuracies. So you can see, I know why this is. Although we are getting 95 and 96% of accuracy for this problem, you will think about, wait, that looks really good. But that's not exactly the best things that you should think about, because if we're using such dummy and a classifier is always predict negative, we are getting 91% accuracy. So basically, you spend almost 30 seconds to train this whole thing. It's just 5% better than 5 or 4% better than random guessing, and dumb guessings here, dummy guessings here. So this actually demonstrates this accuracy turns out to be not a very good and performance measures for the classifier when we are doing this kind of imbalanced data. For example, right here, we have imbalanced data because 90% of data is 0 and only 10% data is actually 1. So that's why a better way that we can do and measure the performances is we can look at the something confusion matrix. So this has a very good idea what we are trying to do here. So we have a talk about this true positive, true negative, and a false positive, and false positive and a false negative, and all these things. So this general idea is to count the number of times of the A and class A are classified as class B for all AB pair. So, and think about what we are trying to do is, so we want to know the number of times this classifier is confused with image of 8 or 0. And you might look at the and the row of and corresponding to the 8 and the columns of the 0 to see how many of that to actually confuse the with 8 and the zeros. Okay, so, and what we're gonna do is we run this whole things right here. So we need to and make these predictions so that we can compare with this actual target. But of course, you can do this everything, test the data set, but I would highly recommend not to do that. And I want to keep this to be untouched for now. And we are just using cross validations, trying to do this k-fold cross validations to do this kind of predictions here. All right, so here we are using a new function called a cross validation predict. It's like cross validation scores, because if we are doing k-fold cross validations, all data has been used at least once and only once as the validation data set. So this prediction is actually done when this data set is being used as the validation data set. So that actually doing this k-fold cross validations, instead of return this evaluation scores as like cross validation scores, it actually return the predictions on each tested fold and a validation fold. So that means we are getting a very clean predictions for each instances of this training set. That means it's always out of sample. So that means, the point that we're trying to make predictions, it's always not in the training set. So this makes sure this can good and have a good qualified and a good quality of out of any generalization errors. Okay, so this basically says the model makes predictions on the data and never solves during the training. So this is very, very important. Then we can just call something called confusion matrix. Then we can compare with the Y train, which is the ground truth, and the Y train predict, and which is our predictions here. You're getting a 2x2 matrix. So this is something called confusion matrix. So you can think about this way. So you can see the first row is considered to be like negative class. And the second row considered to be the positive class. It's like 0 and 1. So you think about this is 0, this is 1, this is 0, and this is 1. Right here, and on this corner, it's called true negative. That means it's the 53 thousands of them are correctly classified as a non-5, and they are non-5 and I classify as 0. For this 687 of that are actually wrongly classified as 5, which is called false positive. That means this should be 0, but somehow I classify to be 5. So you can see right here, this 6, should be 6, but somehow it's being classified as 5. So this is called false positive. So that means we predict to be positive, but that's a false one. So, and this is called type 1 error as well. So this is also frequent questions and frequent asked questions during interview. What is type 1 error? What is type 2 error? And what is false positive? What is false negative, and so on. And the second one is actually consider the image of 5. So this portion right here is, and it should be 5, but it was classified as non-5. It's called false negatives. It's type 2 errors. Then this corner right here, it's and the 3,500, they are correctly classified as 5, and they are actually 5. So this is true positive. So for this right here, you can see this actually have a 5, and a 5 of image is actually non-5, and they are correctly and identified. For these two, they should be 5, but they are classified as non-5. For this 6 should be 6, but was classified as 5. These 3, 5 is actually being 5 and classified as 5, right? So this gives you some idea. The actual precision here, so this whole confusion matrix gives you a lot of information. But if we just look at the position right here, so that means we'll only look as the true positive right here, then divided by and a true positive. So sorry. And I think about the accuracy here. So the accuracy here is we sum the true positive and the true negative and divide by the total number of the data set. That would be our accuracy, right? And they are like, and we talk about the two main things. One is the position, one is the recall. And the position right here is the true positive divided by the true positive plus the false and the false positive, which is the second and the second column right here. So this position will be 3 out of 5 because 3 is correct, and we predict this like to be positive. There are 4 of that, 3 out of 4. So sorry, yeah, 3 out of 4 right here. So, and one way that you can think about is, and so it turns out we can tune all these parameters to have almost perfect positions. And for example, we can always create a classifier, always make negative position and predictions, except for one single and predictions that is most confident about. So, and say you are confident and very confident for one specific image that I can guarantee 99% 99 chances that will be 5. That I'm going to predict that single image to be and to be like 1, and everything else is, and just being like negative. So that way, I will never have the false positive because this like whole thing will be 0 because I only make 1 predictions here, and I only have a 1 single true positive right here. So that will be 1/1. Then you have a 100% positions, but that's not really useful, right? We are only, and that just we are throw away a lot of images should be classified 5, but we are just classified as non-5. So another and a metric is being used is called recall. We have talked about this recalls in the last video. It's also called sensitivity or true positive rate. So you can think about this as being the true positive, same thing, same numerator, but the denominator will be the true positive plus the false negative right here. So these two things. So it's basically think about the second row and the ratio of the second row. So you have a 3 of that. It should be 1 and corrected to be 1, but there are also 2 of that. It should be classified as 1, but was classified as 0. So this is basically 3 out of 5 for the recall. All right, so this is basically and for the recalls, and there's a way to calculate these things of the position scores, and the recall scores give you like this. It's very simple. For this specific problems, we see the position is getting like 83.7%, and the recall scores get 65.1%. So you can see for the recall scores, it's not doing very good job. So that means it should be and classified as 5, but somehow there are a lot of them being classified as non-5. That is the main, I would say, the main resources of the error here. Okay, so with that, it doesn't look very good, and it doesn't look as good as the accuracy that we have. So that means when it claimed to be like 5, it's correct only like 83.7%. And the more important part is only detect 65% of 5. There are like significant portion of 5 being like identified. So, and also we have talked about we can like combine both metric into one single metric. It's called F1 scores. So this F1 scores is basically give you the harmonic mean of the position and recalls. So being calculated as 2 over 1 over position plus 1 over recalls. So this is basically talking about harmonic means for that. So you can think about and the regular and mean will treat all value equally. and however, the harmonic mean and actually give more weight to those like lower values. So it's like well, give like more penalty if one of the value is lower. So this is being and used a lot as like and as a result. So basically, the classifier only get very high F1 score if both of that is high. So you can think about F1 score is even a better one and a better metric than the accuracies. So we can calculate this F1 score. It's 0.73, which is not very good, as you can see right here. And before we talk about how to pick the models, and a lot of cases there are, and in models, there are hyperparameters that we can tune. And for example, in the logistic regressions, you can tuning like different parameters and such that to make sure like everything beyond this parameter is being classified as 1, everything below this parameter is being classified as 0, and so on. That actually give you a good idea. You can think about this whole thing, and this whole parameter is being like 1D lines, and you can set, and all these images is being mapped on this 1D lines, and you need to set the threshold at different point, such that and at like different threshold, you will have a different and the position and the recalls. And for example, if you and set the threshold right here, then your position will be 80%, but your recall is 4 out of 6, which is 70 like 67%. It's basically what we are getting right now. However, if we set the threshold a little bit higher, that we only give 5 that we are the most confident with, then at this point, my position will be 100%. However, my recall becomes like 3 out of 6, which is 50%. So usually if we want to get higher positions by tuning these parameters, by tuning this like threshold, as a result, this recall rate will drops. Same thing, we can get like recall rate and 100%, but as a result, our like position will drop as well. But so this is something called and you cannot have it both way by changing this and threshold. So like increasing position always like reduce the recall and vice versa. So this is something called position recall trade-off, and you can not get both things very high by setting the parameters. But this is not that simple, because under different scenario, you might want to emphasize position. Under different scenario, you might want to emphasize the recalls. For example, if you want to train a classifier to detect the videos are safe to kids, right? You probably would prefer a classifier reject really good videos. That means has a low recall, but keep only safe like ones with high positions. So that means I will probably set the threshold a little bit higher, like to ensure we have a better positions, but I'm okay with low recalls. So that means I'm going to fill out a lot of videos, but I want to ensure 100% the video that I send to kids are 100% safe. So that means I don't want something has a higher recall rate, but let a few bad videos shows up in your product. On the other hand, if you want to train a classifier to detect the shoplifter in those like images, it's probably fine that your classifier only have 30% positions as long as it has like 99% recalls, because you should set your threshold a little bit lower, that you can sure you are getting all these like images as you want it, because it's okay to have several like false alarm, but you want to get all these shoplifter to get caught. So this is the philosophy. So the philosophy is different under different business situation or business models. with the different like and business models, you are going to choose a different and and a different threshold. So that's why on the like first and video we have talked about the business model is very, very important. We need to think for the business, right? So this is something called position recall rate and the trade-off. I think that we have a talk about right here, and this is basically we have a talk about and right here. So I mean, for this like and digit we have talked about, and which is 5, right? So we can check this decision function right on this like some digit 5 right here. And the score that we got is 2,164. That is above 0. If we don't set this threshold, by default, this threshold is set at 0, right? So the 0, that means everything is bigger than 0 will be classified as 1. Everything below a 0 will be classified as a 0. So that's why, so it will predict as a true because it's above 0. But like, and that's the scores that we can, and you can see how we decide. I mean, so which like and a threshold that we can use. The way we can do is, and we can using this cross validation predictor right here instead of using the accuracy right here or other methods. We can just call this as a decision functions to output the scores right here. So, and the higher the score it is, I have a more confident to say this is 5. I mean, it's more negative that we have, and we have a higher confidence to say this is not a 5. For those things that, I mean, this middle here, and there's some like ambiguities, we don't have very high confidence to say whether it's a 5 or not, right? So with these scores, in fact, we can using these scores to plot something called position recall curve that compute the position recalls for all possible thresholds. So this is very important right here. So, and we have this position recall curve that we can just plot out for the Y train, and which is the target variables Y score is our score that we have. We can using this by varying this threat and the threshold, and as a result, we're going to plot this position and versus recall curve right here. So this is the curve of, and this is the recall curve, and this is the position curve. And you can see right here, I mean, it's quite smooth, and up to this point, and they start to have some zigzag right here. You can see the threshold that being chosen here is a 0 by default. So that's why you are getting about 83% of accuracy and 60 something about, I mean, 60 something about the recalls, right? So right here, and we are getting 90%, I guess that's something like this. And also, and you can see they start to change from like 10% of positions up to almost like 100% of the positions. And but at that like high level of positions, you will find out my recall is extremely small. So that means it doesn't make any sense to choose that high like positions here. On the other hand, if we choose very high recalls, our positions will be super small as well. So this is something called and a position and a position recall trade-off. So you want to see like why this is getting and quite bumpy than the recall curve. The reason that the position is may go like sometimes go down when you raise the threshold, and although in general it will I'm always like monotonically increasing, but if we choose a very high threshold here, then like and we can and think about and previously we have 4 out of 5, which is 80%. But if we move the threshold and a little bit higher, you're getting 3 out of 4, which is 75%. So that's why it will drop off, because the number that you predict to be ones will be significantly smaller, then your numerator and the denominator will be pretty small. So that's why it will have some like roughness and zigzags when you choose the threshold to be super large. This is also frequent asked questions during interviews. Why the shape looks like that? Can you draw the shape that makes sense for you? And on the other hand, the recourse can only go down when the threshold is increases, because and that's always and explain why this curve looks so smooth right here. It only gives you like a bumpy curve for the positions. Okay, so and another one that we can plot is we can plot the positions like directly against the recourse right here. So this is the curve that the horizontal is recall, the vertical is positions. And you can see this actually curve is like if you change the like parameter of the threshold, it start to move from like and 100% recourse and start to drop. But in the meantime, your position start to increase as well, right? And this is the point right here. If we choose our threshold to be 3,000, and that's why you are going to get almost 50% of recourse, but 90% of the positions. All right. So you can see our position really start to fall very sharply, and around like 80% recourse. So that's why, and roughly you should probably think about to choose somewhere here that get you about 80% of like positions and 65% of recourse, right? So and all these things and change pretty like dramatically here. So probably this is the best threshold that you should choose, which just happened to be the threshold to be 0 right here. Okay, so for example, if you really want to aim like 90% position, something that in your business model wants you to get this 90% of positions. So what you can do is you can choose the threshold that to give you this 90% of positions. It actually give you like 3,000 and the 370s. That will be the threshold that you can choose to ensure you're getting 90% of positions. But of course, then your recall rate will be pretty low. And for example, and that's something your business model wanted, that's how you can get these things. Okay, so if we choose this everything with that kind of predictions, it actually gives us our prediction, and the position scores is actually 0.9 right here. And you can also do the same thing for the, and of course, at this rate, the recall will be pretty bad, which is below 50%. So that's why, so it's pretty easy to create a classifier, virtually any positions you want. Just set a very high enough threshold, then and then you'll be done. But this won't be useful because the recall rate is too low. In many applications, 48% of recalls will not be great because you are filtering out a lot of positive values, which is a lot of cases will be bad. In the other cases, we talk about the ROC curve and AUC ROC curve. So this is something is also very common tools, which is I would say even more common than the position recall curve that we have just like talk about this. But so this is very similar to this position recall curve. Instead of we actually plot the position versus recall, we plot something called true positive rate, which has the same name of recall against the false positive rate. False positive rate is the ratio of the like negative and instances being incorrectly and classified as positive, and which is basically 1 minus a true negative rate, right? So, and this is the ratio of negative and instances that being classified as negatives. So this is the way that we can and actually calculate those like true positive rate and the false positive rate. So you can just using this ROC curve functions to calculate those values and the corresponding threshold. So in fact, that's the curve that you'll be getting out, and so now the vertical right here is the recause, and my horizontal is my false positive rate. Okay, so as we like mentioned, this part an ROC curve should be like something and off the diagonal here. So I mean this is diagonal line right here. So so this diagonal line says that, and that's the like if we using completely like 50% of random classifier, so that should be like diagonal line. But our ROC curve is pretty much very close to the up and upright corners. So that's why so it's doing like pretty good job. But however, if you want to ensure to getting like 90% of positions, this is something that you'll be choosing here. That will be the threshold getting like 90% of position. You are getting like very low and recause instead, but your false positive rate will be super small right here. And once again, there will be a trade-off, for the true positive rate and the false positive rate. So this is basically says a good classifier is this ROC curve should be as much closer to this point. So those will be and better. So basically a good classifier that stays as far away from the line as possible toward to the top left corner. So as I mentioned, one way to compare the classifier is we can using this AUC, and which is the area under this curve. So a perfect one should equal to 1, and also a pure like random one should be 0.5. So everything should be between 0.5 and 1. So this is, and for this one, we're getting 0.96, and which is not bad. In a lot of cases, you will find out that this ROC curve is very similar to this PR curve. We haven't talked about this. And the rule of thumb, which one we should be using is this PR curve is whenever the positive class is so rare, then you care more about the positive and the false positive than the false negatives. And otherwise, and we can use this ROC curve. So for this and specific and examples, if we look this ROC curve, you will find out, wait a minute, so this is really good. But think about our data is very highly unbalanced, and they are only like 10% of positive. So and this is because like there are so few positive right here. In this cases, then the PR curve will make it clear that this classifier has a lot of room to improve. So like this curve should really close to the top right corner for the PR curve. So for this PR curve, it's quite clear there are a lot of like room to improve to the top right corner. But if we're using ROC curve, it sees like this whole thing will be doing very good job, like the accuracies that we'll be using right here. So that means if our data has like a lot of imbalanced data and the data, particularly those like positive and the labels only take like 10% of the whole total data, probably we shouldn't be using ROC, and ROC may not and fully reflect the whole picture. And instead, and we probably should be using PR curve instead. Okay, so I'm trying to do something like it's close, but not not exactly right here. And for example, if we just trying to using some like random forest, then we can compare its PR curve and F1 score right here. But so we will talk about this random forest things a little bit later. But the random forest class doesn't have the like such kind of decision functions, but it has the ability to predict the probability as well. But you can using this probability as the like and as a weight on the decision functions that we used before. Okay, so what we can do is we can create this random forest things. We're going to using this predict probability features right here. So for example, if we want to make predictions for first an image right here, it says the probability to be and a not a 5 is 0.11 and the probability to be a 5 is 0.89. So that will predict as 1 right here. So which is and exactly what we expected. And also and then there's a lot of things that I mean it's not that kind of like clear here. And you will find out among these images that model being classified as ones with a probability between 50% and 60%. These are actually like 95.4% of the and the positive images. So what does that mean is if we just find out this probability between 0.5 and 0.6 right here, that actually takes about 94% of it and an image to be positive. So that means we are not very confident. And for the random forest, and most of the image to be identified as ones, I have pretty low confidence, only like 50% to 60% of the probabilities. So actually what we got for the 89%, 0.89 probability for this one is just purely and luck as well. Okay, so we can do all these things for this random forest. So it's basically, and we are getting, and we basically plot this like, and the random and a PR curve for this, and for this like random forest. You can see for this SGD classified, I mean, looks like this. However, my random forest is truly close to the top right corner as we wanted. So you can see this is much better than SGD classifier. It comes much closer to the top right corner. In fact, my F1 scores, and you got like 0.92, and my and ROC AUC curve and score has got 0.99. Both metric is doing really good job, right? So so I forgot to mention. So the way I make predictions, if probability that is bigger than 0.5, it will be predict as 1. If it is less than 0.5, it will be predict as a 0, right? So this is just a simple cutoff, as like what we have and had for like and the logistic regressions. But you can see this F1 score is significantly better than this SGD models. And the same here. So you can do all these kind of like position scores. 90, I'm almost like 0.99, and the recalls you are getting is 0.87, which is both are significantly better than the SGD ones. All right, so then the rest of things we're going to talk about is actually the multi-label classes. So we have done and spend like significant time on binary classes, but of course, and the multi-classes is also extremely important. So and sometimes it's also called like multinomial and a classifier. So we want to distinguish between more than 2 classes. For example, even in the MNIST data set, we have a 0 to 9. We have 10 different classes. So there are a bunch of other like classification things that we can use, for example, and the logistic and regressions, random forest, the Gaussian MB, they are all capable to handle like multiple class like and then naively. However, for the SGD and the classifier and SVC, they're also like a version of SVM they can only handle the binary classifications. But we can still using the like binary classification to classify multi-class as well. There are two major strategies that we can use. The first one is called one versus rest. So basically we train like, and for this MNIST data set, we're going to train 10 different binary classifier, each for like one for each digit. We have a 0 detector, 1 detector, and a 2 detector, and so on. If you want to actually classify an image, you are getting the scores for each classifiers. So, and basically you are going to get like, and the scores for 0 detector, 1 detector, and so on until like 9 detectors. And so then you're going to select a class whose classified output is highest scores. And you're going to sort all these like and the scores. You are going to pick and that corresponding detectors with the highest scores. And the reason that means, and the higher the scores, that means the more confidence that we got. So this is one versus rest. You can also do one versus one. That means, and we're going to train the binary classifier as a like each pair of the digits. Like for example, we do 0 and 1s, we do 0 and 2s, and so on, right? But since we have 10 different classes, that indicated we're going to train 45 different and a classifier. So like the main like advantage of this whole process is and each classes only need to be trained on the part of like training set for the two classes that you must distinguish. For example, if you must distinguish like 1 versus 2, then you can actually using these things to distinguish that out. So it's more like subtle ways and give you like more information to classify one versus another. So, and by the end of the day, you are going to do like, and group them together to see which digit actually wins the most, right? So you're going to choose the digit that wins the most on this like one versus one strategies. And also there's some other an issue. For example, SVM scales pretty poorly with the size of training set. And we have 70,000 data set. That's a lot of data set. And it's usually not a good idea to using SVM. So in this cases, and one versus one is much more preferred because I mean, if we have a one versus one, each data set will be like a couple thousands, right? And to train. And if we only have a like couple thousands data to train, it will be significantly smaller than to train the whole data set. And usually those training time doesn't scale like linearly and could be scaled and quadratically. So that's why small training set actually can significantly reduce the training time. So this can train like few and classifiers on large training set if we want. For other binary classifications, usually what we use is 1 versus R. But that, I mean, that's all depends on what we're trying to do here. So like depends on algorithm that we use, it will automatically run the 1 versus the rest or 1 versus 1. For example, right here, so we run this SVC right here. It used 1 versus 1 strategy. It actually trained the 45 binary classifiers automatically. Here, we are not using the full data because if we train the full data, it would take too much time. We're just taking the first 2,000 data set to give you some like idea what we're getting here. So for example, if we train the like first 20 and 2,000 data set, we make this prediction, it will be 5. That's good. But actually, what we do, and we can using these decision functions to make the prediction of the scores right here. What you actually get is you are getting like 9 digits, right? And then like and a 10 different scores right here. You're getting 0, 1, 2, 3, 4, 5. You can see the digit corresponding to 5 has the highest scores, which is 9.3. So that's why we predict to be 5. But one thing that you have and has to be, I mean, and a bit careful here. I mean, as I mentioned it right here, is it actually use 1 versus 1 strategy. But what you are getting is not 45 predictions. So what you actually get is 10 scores. So that means one per class. And this is, and they actually make this 45 and the predictions, one per peer, and the and a selected class that won the most dues, right? So basically, these values is not being calculated from one versus R. Is actually the highest values that you get for one versus ones. And also what you get is the 5 right here. But if you really want to return this 45 scores, you can also do as well. So what you can do is you are going to like force them to output this decision function shape to be a 1 versus 1. Then if you run this, you are actually getting this whole 45 scores if you need it. That and that and I want to emphasize this scores that you got is 1 versus R, but this don't get this to confuse you. SVM that always use 1 versus 1 for training. It's just the way that you got is that you're using 1 versus R as the output, and that will be and a little bit clear to output the values to see this 1 versus R like scores and versus this 45 1 versus 1 scores, because usually this 41 and the 45 scores here, it's not that much informative. But you can use this 1 versus 1 and 1 versus R manually if you want. And for example, if you want to create a very specific classifier, and it doesn't necessary to be a binary classifier, it can create this 1 versus R things if you want. So this is basically the like a 1 versus R classifier. So okay, so I can enforce this SVM right here to using this 1 versus R and a classifier if you need it. You can still do that. You can still make these predictions. If you want. So this actually just create an instance is passing this classifier to and constructors, and so it just automatically create this 1 versus R and classifiers if needed. So this is basically forcing the SVM to using 1 versus R classifier. And of course, and you are getting like 5 as well. But the point is the true estimator in this cases will only be 10 instead of 45. So there are a lot of strategy that you can use to enforcing this to be 1 versus R, or to enforcing this to be 1 versus 1. A lot of cases there are like default choices, but if you want to change that, you can also change that as well. So basically, you can train an SGD and directly on the and a multi-class directly. But of course, this is and by default, I think they are using 1 versus R in the SVM. I think it's a 1 versus 1 in this cases. So sorry, and a 1 versus R in this cases. Yeah. So this actually using the 1 versus R and a strategy here. You are training this 10 binary classifiers, and these decision functions actually return like 1 value per class. But you can see this is not good, and you are actually getting 3 right here, and it should be 5, but somehow being predicted as 3. And you can see right here, you are getting 0, 1, 2, 3, 4, 5. 3 getting 1,800, and 5 getting minus 1,300. And you can see this is not very confident with our predictions. Almost all scores are very negative, but 3 has like a little bit more than 1,800, and the class 5 is not very far away. It's only slightly below than 0, compared to the other and the scores right here. So you can think about this is getting confused with 3 and 5, and which is very reasonable. If you see this image right here, let's say it is 3. It's quite a quite reasonable guess as well. And you can also evaluate this classifier on more than one images. You can do this cross-validation scores if you need it. And this, you are getting this, and accuracy metric is fine right here. You are getting like 84%, 80%, and 84%. So which is okay. But of course, like think about, I mean, if we just do like completely random, there you're getting like 10% of accuracy. So this is like, I mean, still quite good and compared to complete random guessings. But I want to emphasize we're doing multiple classes. I mean, it's not the binary classes, I mean, situation. For the MNIST data set, if we consider the multiple classes, this is actually a balanced data set. But of course, you can do better if you want. So you can do this standard scalar. As we talk about, I mean, this before, you can create a pipeline to do this process. You can do and rescale and scale this out, and that's and the way you like and scale it out, then you perform this whole SGD classifier again. Usually you can see this about like 0.01%. Increases here, you get like slightly improvement by doing and the rescalings and by doing standardizations here. All right, so at last, I want to talk about the error analysis in the multi-class classification problem as well. I mean, you can still do confusion matrix as well, similarly, but this is no longer just by 2 by 2. It will be like, in this case, it's 10 by 10. So this confusion matrix will be and will be a big matrix. And for example, right here, so this actually on the diagonal, that means that should be, I mean, true label, and that will be our predict label. So basically on the diagonal, that's the label, and we predict completed like correctly. But there are a bunch of like off diagonal things. Some of them and predict and big, for example, this is 15 right here. So that is like we predict as like 7, but this actually to be 9. So I mean, these actually get confused here. And of course, and we can just take the ratio here, and you can see right here for true label to be like 9, they are about 7% of the true label to be classified as 7. So which is not really like and good. And you can see this whole thing is not symmetric as well. For example, right here, I mean, so the true and true label to be 3 is classified as 2. That I mean that's like and 5% of the 3s. However, there are 0% of 2s is being classified as 3. So these and this like confusion matrix is, I mean, in general, not symmetric at all. So this is something that you should be and keep in mind as well. So also, I think what you see like I mean this whole diagonal here on the diagonal is quite confusing. So a better way that we can do is we can just negate everything on the diagonal here to see what actually the error comes from right here. So right here, you will find out the error. And for example, this error is 62%, which is, that means, and out of like 0, which is the true and the ground truth, and most of the error is concentrated to be predicted to be 5, right? So this is something that and you should keep in mind. And also for this case is for and out of the true label to be 1, and most of the mistake is being and make to make the and prediction to be 8, right? So this is something that and you should be thinking about. And of course, this is just a way to illustrate it out. And this is very important. Those values are not necessarily mean too much things. And also, we only using 2000 and data point, and you can using the whole data point, which will take quite a bit time to create this and the table or the matrices. But in the meantime, and the most important thing is that once you create these figures, you need to use your own word to write down your observations. So this happens in the homework and the later of the homeworks because not only you need to make the predictions, you also need to discuss your findings, right? And if you make this plot, what does that say? And what does it mean, right? Can you make any kind of suggestions for those models, and how should we improve that, right? And for example, right here, we got big and a big yellow chart here for 0 and 5. That means it make a lot of mistakes for supposed to be 0, but somehow being predicted as 5. So that means we probably need more data of that kind of zeros, and we can train like 1 versus 1 for 0 and 5 to maybe increase increased accuracy for that specific part, and such that we can lower this this percentage. All right, so and we have a talk about this, and these numbers sometimes doesn't match. So the reason these numbers, in this description, and it doesn't match, it's I only using 2,000. I only using 2,000 data points. And of course, if you're using the full data point, you will see these numbers to show up. At the end, so this is just give you some an illustration that we have for the binary classification problems. So let's just plot 3 and 5s, and you can see that and right here 3 and 5 is I think there are it's 5% right here, and 3 and 5 it's 6% right here. So this is basically should be 5, but 6% of 5 is being predicted as 3. 5% of 3 is predicted as 5, right? So this is something that we in mind. So we can plot them out to see how many of that actually being predicted wrong. So you can see right here, the truth, and this should be 3, but somehow being predicted as 5. But you can see those digits. Some of this is quite close to 5. For example, this one right here, and this is quite close to 5 right here. For this an image is supposed to be 5, but somehow being predicted as a 3. And you can see some of this is quite close to 3. For example, this one right here, it's quite close to 3. But think about this image right here compared to this image. One is 3, one is 5. But if you look this way, even for human beings, sometimes we might make mistake for this image to be classified as 3, right? So this is quite important here. And you can see right here, 3 and 5 is the most and difficult part. So that means we might need to think about that we should augment the training set by rotate or shifting the data set such that and we can include and more training data set. In other cases, 70,000 and it may not be enough. We might need to augment and the data augmentations to make this model to to be learned to be more tolerate and that kind of variations if we need it. So this is something that we're going to talk about in the neural network classes, and this turns out to be one of the things that we necessary to do this kind of data augmentations if needed. So this just here, we're not using neural networks, just trying to using a very simple things to illustrate the whole idea of those kind of performance metrics on binary classification and the multi-class and the classification problems. All right, so I think that's everything I want to talk about for this specific lecture. For the first part, we are using and we talk about concepts. For the second part, we are using code to illustrate the idea we just mentioned on the concepts. So this has a two peers, and like these lectures is quite long. So I want you to go back and forth to go through this note and notebook and run line by line to understand all the concepts by yourself. This is a very important. Many of concepts is being asked very frequently during the data science job interviews. All right.